Club, NVCTI ITS in Dhanbad, welcomes you all in this guest webinar on the topic Convergent Manufacturing from Biology to Digitalization. And our guest speaker for today is Dr. Salil Bapat. Dr. Salil is a research scientist in mechanical engineering at University of Purdue. I welcome Dr. Salil. We are glad to have such a knowledgeable speaker on the board. And yeah, okay. So with this, I invite Dr. Salil to start today's section on convergent manufacturing.
Thank you. And let me know when you can see my screen. Put it in the presentation mode. Do you see
Yeah,
the presenter view or the full screen?
yeah, it is visible.
Okay, but do you see two slides or do you just see
Yeah,
one
two
big slide?
two slides are visible. It is not in full screen.
Okay, it's not in. How about now?
Yeah, now it's on full screen.
Okay, excellent. So I'm using two screens, so that's why it sometimes becomes a challenge. So, anyways, so thank you for inviting me for being a part of your smart manufacturing. Okay, sorry. So thank you for inviting me for the Smart Manufacturing webinar series. My name is Salil Bapat, and as I was being introduced, I am a research scientist here at the Purdue University School of Mechanical Engineering. And these slides are made in conjunction with a couple of our my supervisor, Professor AJ Malche, and is a work of over last 8 years. So at the end of the slides, you would see multiple publications from our group that you're most welcome to look into. And this topic that I have chosen and what I'm going to discuss with you is slightly different than what probably you have imagined. And the purpose is that you are budding engineers and scientists coming from IIT Dhanbad. And I wanted to keep the presentation not in terms of presenting my research, but in terms of identifying what are some of the upcoming things in the field of manufacturing, and where, if you do decide to go for, say, graduate school or continue research, what are some of the areas that you would be working on. So that is the way the slides are arranged. And let me begin with the presentation. And thank you, first of all, for joining late at night. I know I'm running into your dinner time, but hopefully you would find the presentation engaging. So before I go on to presentation, just wanted to highlight where my background is and what my research interests are, and what we as a part of Materials and Manufacturing Research Lab at Purdue with Professor AJ Malche are been working on for last 10 years. So just a quick summary, I am an undergraduate degree in material science and engineering. So I'm not mechanical engineer by my undergraduate degree. I got my degree from IIT Kanpur. And in fact, the director of your institute, Professor Raju Shekhar, he was there at the time, and I was one of his students. So I did my undergraduate in material science. My PhD topic was in tribology. If you're not aware, that is study of friction and wear, to study surface engineering, how surfaces behave under the application of lubricants, how the surface texture plays a role, and so on. But at the same time, I also worked on what is called as bio-inspired science and engineering. And the research here at Purdue has bio-inspired science as one of the founding principles of whatever we do. And next couple of slides, I would present the research on bio-inspired science, that what we have published, and how that serves as a platform for what I'm going to talk today. So with that, just a brief example that in nature, you would find different systems, different animals, different plants that have designed certain surfaces to give a functionality. So give me 1 second while I pull up the laser pointer. So on the top left, you see lotus leaf, which is a super hydrophobic and self-cleaning surface. In the middle, you have a morpho butterfly. which has a radiant blue color, but that color comes from the light interference and not from the pigments. Same with the peacock feathers. Then you have gecko feet, which basically allows gecko to climb on multiple surfaces without use of adhesives. You have desert beetle, shark skin for managing friction and drag in water, snake skin, and moth eyes for anti-reflection. So all these features that you see in biology, the functionality that is imparted by these are listed on your background. So friction, drag reduction, anti-reflective coatings, dry adhesion, superhydrophobicity, so on and so forth. And where can this be used is actually creating products from it. So you have a excuse me, you have a super hydrophobic coating, structural colors being used as a security purpose on currency notes, structural colors for contact lenses, gecko grippers for in-space applications. So you have an astronaut testing under zero gravity using gecko-inspired grippers, cutting tools based on snakeskin surfaces, antimicrobial surfaces based on shark skin, and anti-reflective coatings on the TVs. Specifically, snakeskin is an example that we have studied in our lab and have published a couple of papers over the last 4 years. So if you look at the snakeskin has hierarchical texture, what we call as. What it means that it has macro scales, hexagonal scales on the ventral surface where the snakeskin touches the ground. And if you zoom in, you would see micron scale directional texture. So what that does is that gives a friction and anisotropy behavior. What it means that snake can move forward easily, but when it doesn't slip backwards because it has a higher coefficient of friction in the backward direction. So what we did on inspired from snakeskin is that we investigated the laser powder bed fusion, which is one of the additive manufacturing technology, metal 3D printing, to create snakeskin-like structure. And we measured frictional properties of that snakeskin-like texture. As you can see, you have a surface texture that looks pretty much like what you would see on the snakeskin, directional. And the frictional properties also are anisotropic, that depending on the direction of motion, your friction is either higher or lower. So we proved that there is a frictional anisotropy that comes from the surface texture itself. With that, let me go to the introduction. So this was the background on why we are looking into bio-inspiration. Let's go into the brief introduction of the convergent manufacturing. So as you're familiar, over the last 2 years during the coronavirus pandemic, that this was the impact of coronavirus on the supply chains and the economy in general, where you have operational integrity of operations compromised. Pretty much all the factories which were focused on physical contact, for example, say meat packing in US, were hampered because people were just not there in person to work. But at the same time, you have rising digital technologies. And as you can see from Zoom meetings and everything that has digital thread helped compromise some of the ill effects of the coronavirus. But where we are really going is that what happened or what coronavirus really taught us was to be resilient. And the picture summarizes what we are, where we are now, is that you have an impact of coronavirus, but what we need is a resilience in the manufacturing enterprise or manufacturing supply chain. To that, keep that as a background, and now try to look into definition of how National Institutes of Science and Technology defines smart manufacturing. So smart manufacturing per NIST is defined as a fully integrated collaborative manufacturing system that responds in real time to meet changing demands and conditions in the factory, in the supply network, and in customer needs. So when we are talking about smart manufacturing, you also need to take into the aspect of sustainability into the picture. So this is the picture that represents Industry 4.0, which is typically termed as the smart manufacturing part. But you also have to think about the societal, economical, and environmental impact of incorporation of Industry 4.0. The three key things that I took from this slide are highlighted below is that your system should be adaptable, it should be resources and energy efficient, which sometimes comes from the fact that you use locally sourced materials and you locally produce. So you might have heard terms such as uh, uh, modular supply chains. And what it really means is that you produce locally on and you sell locally so that you have a smaller supply chain. So if in case there is any disturbance such as coronavirus pandemic, you are not susceptible to a longer supply chain and delays. So, and it also collaborated. So let me ask a question now that where do you see a system that is adaptable, that is resource and energy efficient, and that is collaborative? It's in nature. So you look in nature or biology as a smart manufacturing factory. So I gave you a bunch of examples from nature, from lotus leaf to shark skin to snake skin. But we should really view nature as a smart manufacturing factory because all the three things that I highlighted before, adaptability, the resources and energy efficiency, and the collaborativeness is found in nature. So with that, let me put a background of what we can learn from nature and how we can apply that to manufacturing. So this is a representative picture of the resilience in nature. Remember, I highlighted the word resiliency when talking about smart manufacturing. So the definition of resiliency is an intrinsic property of a system to resist and slash or recover and slash or adapt to a new and improved state in time, much smaller than the overall lifetime of the system under the known or unknown perturbations. And again, I highlight the three same facts that I highlighted before, that it should be adaptable, resource and energy efficient, and collaborative. So with that in mind, we looked into nature for strategies that impart resilience to natural system. And if you're not familiar with this specific term, this might come in. It's called a biologicalization in manufacturing. Uh, the International Academy of Production Engineering, also known as CIRP, has championed this term called biologicalization. And what it really means is that it's going from biology to manufacturing. There are different aspects of it. One is bio-inspired, one is bio-integration, and one is bio-intelligent. And all these three would play a role when you talk about smart manufacturing systems. So with that being said, let us look into nature for motivation and what nature uses as some of the strategies to impart resilience to the system. So if we look into nature, toolbox. So if you're familiar with tools and toolbox, you have a toolbox that, say, mechanical engineering, or you go to a machine shop, you have cutting tools, you have filing and finishing operations, different tools, they are there in your toolbox. So what is there in nature's toolbox that gives certain species resilience and adaptability? So for the purpose of this talk, I'm going to focus on top 5 of the listed tools: the selection and organization of size and shapes, management of defects, distributed structures and systems, sensory networks, and division of roles. So next few slides, what I will do is, next few slides, I have a case study from a nature that talks about one of these parameters or tools and its manufacturing equivalency, or how it can be used in a manufacturing setup. So first case study is the management of defects and shapes and sizes. So the example from nature is a human tooth. And if you have not seen the architecture of human tooth, it is a beautiful hierarchical structure where going from a nanostructure to microstructure to macrostructure, you have multiple defects that come into the picture. Also, this is a system that uses ceramics. So if you think about tooth goes into very highly corrosive environment, but it still retains its toughness. And that comes from the hierarchical structure that you have defects that are managed in such a way that your cracks do not propagate at a longer distance. And that also has to do with the materials. Remember, I'm a material scientist by training. So a ceramic and a polymer material, the layers that you see, and this is another example from nature, is mother of pearl or nacre. So where you get the pearls from, the shell of the mollusk that has very high fracture toughness, and that toughness comes from the layered architecture and the polymeric substance in between. So two things to note from this slide is that you have multiple materials, so composite materials, and you have scale and management of defects. So at what scale you're looking at. The key highlights, again, as I said, hierarchical designs, composite materials, and utilization of locally available resources. If you think about it, nature does not use steel, but it still is able to deliver hard and tough services where it needs to. And that is because nature uses locally available materials, the carbon-based materials, the polymers, and the ceramics like calcium carbonate. But at the same time, it manufactures it in such a way that it gives the properties that you need, whether hardness or toughness or whatever is needed. So let's take an example of where this can be used in manufacturing. The engineering example on the right-hand side you see is an example of cutting tools, which follow the same principle that you have a multi-layer structure of titanium aluminum nitride and a ceramic. So you have a multi-layer structure either at a nanoscale or a micro scale that is going to resist the propagation of cracks. So it is similar to what you would see in the left-hand side where you have a nacre-like structure. Second example, and this I really like this figure because it tells you from nature, from submicron scales to micron scales to macro scales, how the design architecture is similar in nature. So on the right-hand side where my cursor is, I hope you can see my laser pointer. You have a coronavirus type structure, which has a centrally spherical location and bunch of spikes. This is an image of coolants from tree at a micro scale, 10 micron scale bar. Very similar structure, multiple spikes, and this is on a macro scale, a dandelion flower-like structure. The purpose here is that you have multiple distributed networks to impart redundancy to the system so that if one of these fails, there is another one that is available for connection, similar to the virus also. So effectiveness over efficiency. This is very important because if you think of your traditional engineering approach, we always say we want to have higher efficiency. But in nature, not only efficiency is important, but effectiveness is also important. Efficient does not always mean effective. And effective is important when you talk about solutions. So let's take a parallel example of engineering where distributed structures would be used. And here I give an example of systems and system of systems, that distributed supply chains, what I was mentioning, local supply chain versus large global supply chain, how by distributing smaller and smaller supply chain networks, you can be more resilient. Moving on, a third case study is sensor, and this is something that we would come back at a later stage. The example from nature are two examples actually. On the left-hand side, you have a Venus flytrap, which senses an insect coming inside and closes its door and basically uses the nutrients from the insect that is being captured. On the left-hand side, you have a touch me not plant that you might be familiar with, that when it touches, it closes for protection. So you have a sensory system, a robust sensory system in nature that can sense any potential threats, and appropriate action can be taken for survival. And resilience is imparted through effective adjustment by sensing and decision making. So you have to sense and you have to adapt. Now, where this can be used in a manufacturing setup is, again, coming to the topic of the digital twin and smart manufacturing. You have seen Industry 4.0. I'm pretty familiar. You have listened to a lot of talks on Industry 4.0. And that sensors and process monitoring is very crucial in the Industry 4.0 setting, where you can collect the data, you can analyze the data for any adjustments to be done, and you can take an corrective action if needed so as to be more optimized in terms of process efficiency, process products. Fourth example, now we are, so if you notice, my previous examples were at a component level. Now I'm going to a process level, and now I'm going to a system level. So a colony of ants is resilient because the roles of ants are dynamic. So say, for example, ants are getting sugar from some source, and they are carrying the sugar to their nesting site. If for some reason that pattern is disturbed, or if there is a disturbance, the ants still can follow the trail because their roles are changing dynamically, and they also have a sensing system where the pheromones that are released from ants are sensed by the antennas, and you can still have the same track. So the colony of ant as a system is resilient because it can reconfigure and adapt in the wake of a disaster and still have the same efficiency in terms of carrying its task, which is carrying a source of sugar from one point to other point. Now, where can this be used in an industrial setting from a manufacturing perspective? Is an engineering example of dynamic job scheduling, where what you're seeing is that based on the changing conditions of materials, scheduling, and resource constraint, you can have modular machine tools to reconfigure the process flow. And again, the whole idea is to be more flexible as opposed to more robust. And flexibility gives you the resilience that you need. So 4 examples from nature, 4 counterparts in manufacturing. So where do you see the role of digitalization? So remember the topic that I chose, or the title that I had given, was going from biology to manufacturing, and then going on to convergent manufacturing. So what is the role of digitalization? So let's come back to the definition of digital twin, and this is the definition that is being defined by American Society of Mechanical Engineers, ASME, which defines a digital twin as an exact virtual copy of an object, a product, a piece of equipment, person, process, supply chain, or even a complete business ecosystem. So the point that I want to make is that digital twin does not necessarily be of a component or a product. It can be of a process, it can be of a process chain, and it can be of the whole shop floor, for example. I have highlighted a couple of important things that are needed for creating a digital twin. Of course, you need to have a sensor technology so that you can sense any changes in the environment, much like what you talked about in nature, and you can monitor the system. Also, what you would need for a digital twin is a capability to simulate and model. So the interaction with the environment. Say, for example, the example that I gave you of snakeskin-like texture, that is a part digital twin, in my opinion. That you have a digitized version, a CAD file of snakeskin-like texture, but what I don't have is the capability to simulate or model how that digital structure interacts with an environment. So to have a complete digital twin, you need to have a multiphysics simulation or a multiphysics modeling capability that is able to interact with the environment and come up with how the system would react, or how the component would react, or how the process would react. And also, and that brings me to the last point, is that the adjustments can be made to the digital twin to see how the system would change in real life before making any changes to the original system. Now, specific to the manufacturing, so these are the 7 attributes that 7 digital twin application for manufacturing identified by ASME. And out of these 3, at least from a research perspective, not from a commercial industrial setting, from a research perspective, a product design, process optimization, and predictive maintenance make the most sense. That this is something that you would encounter if you're doing research on a digital twin in a university level at a lab scale, not at an industrial scale. So I would request one thing from you. Let me know if the audio is, can you hear the audio from this video I'm saying? Oh, looks like it is not. Even I cannot hear it. Can you hear anything?
Yeah, it's not audible.
It's not audible? Huh.
Yeah, it's not
Let
audible.
me check the sharing options. Just give me one sec. Share sound. Perfect.
The key.
Is it audible now?
Yes,
It is audible.
Okay, excellent. So let's take a step back. Apologize for the technical challenge. But let's take a step back. What I was saying was that in an industrial setting, how can I go back to the slide? Yeah, on a lab scale setting, a digital twin for process optimization, product design, and predictive maintenance. And I'm not going to play both the videos, but you're more than welcome to listen to it, and I'm happy to share the links from the YouTube. On the right-hand side, you see a digital twin that is capable from a Dassault Systems software. And on the left-hand side, you have Siemens. There are other industrial softwares that would let you do the digital twin from a manufacturing perspective. I think ANSYS has one. And if I remember correctly, there is one more. I'm skipping the name. But let me play the video and I'll continue the presentation.
The key. Becoming a digital enterprise to meet the market requirements. This means integrating and digitalizing the entire value chain and creating a powerful digital twin of product, production, and performance of real production and real product. The digital twin merges the real with the virtual world. The digital twin product enables manufacturers to design, simulate, and verify products.
So this is what I was mentioning before about the capability of having a multiphysics model to simulate and verify.
Digitally, including mechanics and multiphysics, and to manage embedded software, and also develop integrated electrical and electronic systems. This concludes the specification of the product. All the data is then used for the creation of the digital twin production. Manufacturers can plan and validate their production process, create the layout and select the equipment, and simulate, predict, and optimize working conditions for humans and the manufacturing assembly processes. After automatic generation of the PLC code, virtual commissioning allows validation of the automation in the virtual world, which enables fast and efficient commissioning on site. Even revolutionary designs can be simulated with additive manufacturing and are created with integrated robot controls the same way. Next, virtual becomes real. The PLC code is transferred to the devices on the shop floor. Totally integrated automation enables efficient and secure production. And SIMATIC IT allows scheduling and execution of work operations and quality inspections. Monitoring of all machines, everywhere and anytime with MindSphere enables the creation of the digital twin of performance of production and product. This makes it possible to analyze and evaluate the performance of the real production and of the real product. This allows feeding back insights to continuously optimize the digital twin of product and production. This leads to the continued improvement of production and the product in the real world.
So what we saw in the video was going from a component to assembly to the product simulation and to the optimization. But that is a part of digitalization. Now, I want to take a step back, and I hope the slide works. So where are we going in the future? It's well and good that you have a bio-inspired technology, you have a digitization, you have a digital twin that you're capable of going from product to process to systems to actual operation. But moving on beyond Industry 4.0 and coming back to the whole thesis of this talk is the convergence. So National Academy of Engineering defines convergence as convergence of life sciences with physical, chemical, mathematical, computational, engineering, and social sciences is a key strategy to tackle complex challenges and achieve innovative solutions. So where we view where we are going is not one stream, this versus that, biology, engineering, science, society, economics, everything. It is all converging together. And digitization is part of it. So what we see is going towards convergent manufacturing. So let me give you an example. Say you must have heard talks about us going into space. And if you're going into space for a habitat, you need to have very extreme conditions, but you need to have a robust system that is capable of not only sensing the harsh environment, say on Moon or Mars, but at the same time have a capability of delivering a specific function on demand and on site. So if you look at a pyramid, you have advances in manufacturing, science, and engineering. You have multifunctional applications, and at the top, your end goal is to have an on-demand, on-site delivery. But what is missing is that there is a gap in between, and that gap, as we see, is processes and materials. So what I mean by that, I took an example of human tooth, and I mentioned the fact that you need to have multi-materials. You need to have composite materials, a ceramic and a polymer, or a metal and a polymer. The manufacturing science or the manufacturing processes that we have at hand, at least at this time, are siloed. What I mean by that is that you have a special manufacturing system for metals. You have a different manufacturing process for polymers or ceramics. And there is no one manufacturing unit that would basically process both different types of materials and different types of processes. So this is where we see what we need in the future is the gap of hybridization in materials and processes in manufacturing. And what that leads to is a model of what do you want from smartness in manufacturing. You have implementation of sensor and monitoring. We talked about that through the digital twin part. You have simplicity in science and engineering. So this is where the bio-inspiration comes from. Use of locally accessible materials and expertise for sustainability. And you need to have a redundancy and communication for resilience. So this is the model that it's not mutually exclusive. There might be other things that would be added as we learn more, but at least this is a good start. So with that, what we had I think this was in September 2021. We had a workshop on Purdue campus on convergent manufacturing. And this is the National Academies of Science, Engineering, and Medicine in the US. They recently published this report, so this document is available online. It's called Convergent Manufacturing, the Future of Additive, Subtractive, and Transformative Manufacturing. And just to take one excerpt from this report, it defines a convergent manufacturing platform as that synergistically combines heterogeneous materials and processes. Remember the gap that I was talking in the previous slide. For example, additive, subtractive, and transformative processes in one platform. The platform is equipped with unprecedented modularity, flexibility, connectivity, reconfigurability, portability, and customization. All of this was what we talked about, the resilient part. The result is a one manufacturing platform that is easily reconfigured to output new functional devices and complex components or systems. This manufacturing system also converges the integration of physical components and digital models along with the sensor network for process monitoring and production. So essentially what I had spoken, from bio inspiration to strategies for resilience to the digital twin application, all is now getting combined into what we term as a convergent manufacturing. And this is where we would go from Industry 4.0 to, I believe, Industry 5.0. And just a quick recap or a quick pictorial view of what I just described, that you're looking into designs from biology to digitalization, your designs, materials, and processes through multiple tools that are available to you. So tools are, for example, 3D printing, different type of machines, artificial intelligence, robotics, digitization, and all that. So these are your tools. So you're going from designs, materials, and processes to a specific target population that is now customizable. And before I end this talk, I have just one more slide to not forget the societal aspect of smart manufacturing. And you might, I don't know how many of you are familiar with The Simpsons, which is the longest running TV show in the US, but
I'm a college man! I won't need my high school diploma anymore! I am too smart! I am too smart! I am too smart! I am too smart!
So what I wanted to show is that just because you say something is smart, what exactly is smart? Smart manufacturing may be good for one, but if it is going to create a fire at another end, is that really a smart manufacturing? Same thing, digitization. Going digital would allow you to go smart and have a production system that is, say, self-optimization. But what happens to the people or small businesses, those they don't have a digital capability? That would create what is called as digital divide. And the plot, this is from 2021, that you see that there are 4.9 billion individuals that have access to internet, but almost half of this number, 2.94, more than half, still don't have access to internet. So if that is the case, is going digital 100 completely smart? That's a question I want to ask. So the point that I'm trying to make is that digital is part of smart manufacturing, but smart manufacturing does not necessarily mean digital. And with that, I would like to conclude my talk, and I would be happy to answer any questions, reflections, brainstorming, whatever you want to term it. These are some of the publications from where I prepared my slides. So if you're interested, I would be happy to send you all of these papers that are published, and a couple of them are coming up soon. Thank you.
Thank you, Dr. Salil. Uh, Thank you for such a great session, and we are having a good insight of the convergent manufacturing and its biological aspect. So now we are having some of the questions for you and
Sure.
inside. Yeah, so in one of your slides, you talked about the dynamic scheduling of jobs. So, can you explain further means what is it and how does it impacts the means the whole process, manufacturing process?
Sure. Let me just go back to my screen sharing. I mean, some difficulty. Just give me one sec. This slide, right?
Yeah, this one.
Yeah. So let me switch my presenter view. Okay. So the dynamic job scheduling, what is talking about? So this is the paper. I can that is from where I took this figure. But essentially, you have a digital thread, cyber shop floor. Then you have a transport layer where you have a connectivity between digital and physical, and you have a physical shop floor. So what it's trying to do is that depending on what resources are available, say for example, you have a shortage of a certain material. Now, your process sequence originally called for using that material and manufacturing the product. But now you sense that this material is running short. What I can do, or through this network that the digital twin can do, is that it can sense that you're running short of a certain material, and instead of using that material in a process sequence, you can reconfigure the shop floor in such a way that while you're working on getting this material back, you do something else so that there is no downtime. So that's what I meant by dynamic scheduling your jobs, that you have a certain jobs that are being performed on a physical floor, but those are dependent on certain restraints. For example, manufacturing, or there might be shortage of workers, or there might be a shortage of certain capacity that is needed to manufacture a product. So what dynamic job scheduling would do is that it would allow to make sense of what is available at a given time t and perform the best set of scenarios in manufacturing on the shop floor. Does that answer your question? Does that make sense?
Yeah, yeah, means I got the idea. So it is like that, just changing all our changing the job
Yeah,
according
that,
to the
that
dynamic situations.
right, right.
Yeah,
So the key term is the reconfigurability of the system. But let me take one step back, and I did not explain this, is to have a reconfigurable system. Say, for example, your shop floor is manufacturing a plastic injection molding component. Now you find out that a certain plastic that is needed is running low. And now you want to switch to, say, printing a dental ceramic implant. If you have a manufacturing system that is, say, 3D printing plastic, and now you want to do a ceramic implant, you cannot do that in a given situation. So you need to have, you can do that technically with, I mean, you can say that we want to do this because it is more efficient, but you need to also have the capability from the manufacturing process standpoint. And that is where the motivation from conversion manufacturing comes in, that it is not limited by the materials, that you would have a manufacturing conversion manufacturing platform that depending on your dynamic scheduling, you can either process polymer or you can process ceramic or you can process both. That is a capability that we don't necessarily have at this stage.
yeah,
Does that make sense?
yeah, it makes sense. So
So
we'll
just
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 find
to
the efficient possible solution.
right. So just to bring it more forward, say you have a metal 3D printer. That metal 3D printer does not necessarily print polymer. So if you want to now have a dynamic job scheduling and now print a polymeric system, you need to completely change the printer, or you need to go to a different printer. Whereas in a conversion manufacturing setup, that what I mentioned, that you would have the same platform, same one device that is able to now, using some reconfigurable tools, is able to configure itself so that now it can print the metal using the same system. Oh, sorry, print polymer using the same system. And that is a limitation at this stage, that you don't have a manufacturing process or a system that is capable of combining processes for different materials. So that was the gap that I identified in one of the next slides, that there is a gap between what you can do with manufacturing processes, but what you can do with different materials. Any other questions?
Yeah, one more question
And
from the side. And
go ahead. Go ahead.
this, yeah, talked about digital twin. So, yeah, if we want to make digital twin of a process, so it means how efficient it can be, means on what parameters its efficiency will depend. So, will it be practical to achieve efficiency? Means that accuracy that will ultimately beneficial for the industrial aspects.
See, that is where the research is needed at this stage, I would say. Uh, what I would say is, it is there, the capability is there, but it is limited in a sense that what it can do. So, say for example, and I go back to additive manufacturing example. Say for example, I have an additive manufacturing setup from a company A. I have a digital twin for that additive manufacturing setup for company A, using the process that they use, using the materials that they use. So I have a digital twin. I have a capability of simulating the environment. I have the capability of modeling how so say for example, laser interacts with the material. But that does not necessarily mean that if I go to a same manufacturing, metal 3D printing, but now with a company B, which is a slightly different setup, slightly different approach to printing, or slightly different approach to consolidation, I may not have that, or that software that I'm using is not compatible with machine B, with company B. So it is not universal. So that is the challenge. That if you want to be truly harnessing the power of the digital twin, you need to make sure that you cover all the bases, see that you can manufacture all the different materials. So you need to have the capability of a database that has all the material properties that you are going to use. You need to have a database that is capable of simulating, say for example, it is a laser-based system, how laser interacts with that specific material. You need to have sensing capabilities that can real-time update, so real-time monitor the melt pool, for example, in a metal 3D printing process. And it exists in parts at this point, but there is research going on in terms of making it better. And that is the current challenge, that you need to make it more and more efficient. Because one of the key challenges, remember I talked about digital twin, one aspect was you have to have a CAD model. That is well and easy. The second aspect was the sensing and monitoring. That is not as straightforward when it comes to additive manufacturing setup, and I'm pretty sure for other systems too. Say for example, you're using a cutting tool and you're cutting a certain high entropy alloy or a critical alloy. Typically, when you do cutting, you have flooded lubrication, or you have a coolant. Now, if you have a coolant and you have a camera that is monitoring the cutting zone, how reliable is that system, that even in the presence of coolant that is liquid, that you're able to sense what exactly is happening at the cutting tool? That reliability may not be perfect at this stage. So you need to have other techniques. You need to have other monitoring techniques. Maybe you can have a non-destructive valuation or ultrasonic evaluation. But then the challenge is that how can you take data from an ultrasonic machine and analyze that data to get a meaningful inference that you can now model in an artificial intelligence perspective. So there are multiple parts to answer your question. There is no one answer because there are multiple parts and each part needs to be optimized for its maximum efficiency. Does that make sense?
Yeah, it's clear. One more last question from our listeners, and
Sure.
that is, yeah, you told that it is like hybridization of the materials and process in physical, chemical, mathematical. So all these things means how can we differentiate these from all the conventional things happening in industry today? Is there also all these things are happening and just like a similar way? So how does the convergent manufacturing is differentiated from that?
That is a good point. And what I did not mention when I talked about conversion manufacturing, I talked about the capability, but I did not talk about what is traditionally called as workforce development. And just like budding engineers like you all, uh, say you come from a mechanical engineering background. Traditionally, when you say you have a mechanical engineering, your choices are limited in terms of where you can go next. But what we are saying is that for conversion manufacturing, there is no silo, there is no mechanical engineering versus chemical versus biology versus food. So we have projects at this point in our lab that we are working on cellular agriculture. What it means that you manufacture meat using a tissue engineering approach, but completely in the lab. And so that to me is the convergence, that you're trained as a material scientist or a mechanical engineering, but you're working in agriculture and food. And it is not straightforward that there needs to be certain gap. Then you say conversion manufacturing. That does not mean that all the workforce development, all the educational programs are completely aligned with that. And that is what should come next. But that is a very good question. What you say? So what is happening in the industry? That industry eventually, I hope, would catch up with this concept of truly interdisciplinary or convergent nature. But that also needs to be complemented on the educational side.
Yeah.
So one thing I have learned, just to add one point. One thing I have learned is that what you do in your own research is it's very transferable to different fields. And we had a very interesting realization. I think right at the start of pandemic, I came across an image that was a histochemical map of meat. And that looked exactly like what I would see for a microstructure of steel. And it just blew my mind. It's like, okay, this looks like a very familiar steel microstructure, but it is not steel, it is meat, a muscle tissue, but it has the same architecture. Any other questions?
Yeah, so no more question. Now let's conclude this session. So
I,
thank you,
I
Dr.
hope I hope you
Yeah,
I hope you had a little bit of insight in terms of where we are going. I deliberately wanted to
yeah,
have the presentation in such a way that you have a food for thought, that you have certain things that you can think about, that if you want to go ahead for a grad school or if you want to conduct research, what are some of the new and upcoming things that you can focus on? And I hope that was helpful.
yeah. I mean, this session gave us a lot more insight about that, and your good presentation and all that examples of that ants and tools were also very good. And so,
Glad to hear that.
thank you. Yeah. So thank you, Salil, Dr. Salil, for giving your time, precious time for such a great session. And yeah, after this, let's end this session because no more questions are from our side. So
Sure. Thank you. I
have a nice day.
appreciate you listening in late in the evening.
Yeah,
Thank you.
thank you.